So in this module, Module 7, we will be discussing energy, more specifically mechanical energy. So we'll have two parts to this video lecture. The first part, we're going to cover the basic definition of energy, specifically mechanical energy, and the two types of mechanical energy, kinetic and potential energy, the change in energy as defined by work. Talk about the first law of thermodynamics and the conservation of energy and the work energy theorem. Give an example of how work is performed during landing from a jump, and then cover real briefly the mechanical efficiency and economy of human movement. So what exactly is energy? If you Google the definition of energy, you're probably going to get maybe 9 or different definitions, especially among physicists. But the simplest definition I found is that energy is a state of matter that makes things change or has the potential to make things change. And make things change is just a simple way of performing work, or of saying performing work. It is a state that characterizes a system or body to perform work. And there are different types of energy. There's chemical, thermal, mechanical, acoustic, electromagnetic, nuclear, and if you've taken physics or chemistry, I'm sure you covered the detailed mechanisms by which energy is performed. But for our course in biomechanics, we're mainly interested in mechanical energy. If you've taken exercise phys, you more than likely will cover chemical energy. But in this case, we're looking at the mechanical energy, which is the energy associated with the mechanics of human movement. This includes displacement, velocity, acceleration. And the two types of mechanical energy is what's known as kinetic and potential energy. Kinetic energy is the energy due to motion. So if an object is in motion, it has kinetic energy. Whereas potential energy is the energy of an object's position or deformation or configuration that has the potential to convert to kinetic energy. So if I'm holding, I don't know, a dumbbell up in the air that's about 6 feet up in the air, it has the potential to change to kinetic energy once I let go. And that potential energy, that gravitational potential energy, which is really what we're only going to cover in this course, is related to its position to the ground or its height. There's another type of potential energy called elastic potential energy that is related to deformation or the spring constant of a spring. We're not going to cover that. Your muscles and tendons and ligaments have a certain amount of elasticity, and that is measured by what's known as elastic potential energy. So, I'm not going to cover that. That's beyond the scope of this particular module and course, so we're only going to concentrate on gravitational potential energy. Now, gravitational potential, as I mentioned earlier, is dependent on the object's height, because we know that gravity is only in the vertical direction, and it is directly proportional to the object's weight, that's mass times gravity, and its height. And so if you do the math here, you get Newton times meter, you get Newton meters, but we know that Newton meter is used to describe the units for torque, so therefore for energy, we actually use what's known as the joule, or J. So the energy for when the object is in motion is known as kinetic energy, and it is directly proportional to 1/2 its mass times the square of its velocity. So by changing an object's velocity, you can also subsequently change its kinetic energy substantially, right? It's because it's squared. So if it doubles, the velocity doubles, you literally quadrupled its kinetic energy. Okay, kinetic energy, there's two types. There's depending on whether you're looking at linear motion or translational motion or rotational motion. If it's rotating, you're looking at angular motion. It has rotational kinetic energy that is also directly proportional to 1/2 its moment of inertia times the square of the angular velocity. If you recall that moment of inertia of a rotating object, it's resistance to angular motion, its inertial property to resist a rotating object. Don't worry about that too much. We're mainly going to concentrate on translational energy. translational kinetic energy. So the change in energy is what's known as work. So work is performed when an object moves or displaces due to an application of force. The energy to the capacity to perform that work is known as energy. So work is a transfer or a change of energy, and that's governed by this nice simple equation here, where work is equal to the product of the force of application and displacement. If you recall, displacement is simply the change in position. That's the final position minus the initial position. So therefore, no work is performed if displacement is zero. If something were to move and it took this really crazy path, but ended up on the same position from which to which where it started, so therefore no work is performed because displacement is zero. Now, work is a scalar quantity, meaning it doesn't have a direction per se, but it can be positive or negative depending on whether or not the system is generating energy or absorbing energy. And no matter how much the physical effort was imparted by the person, no mechanical work is performed if it wasn't displaced. Very important. And I'll give you an example here. Say you have Jane here, and I don't know why I use Jane quite a bit, but let's say Jane is moving up a flight of stairs, and each flight going up and going back down is 10. So 3 meters total in total height there. So we're going to use this example to describe the difference between positive and negative work. So let's take the first one, going up. Going up the flight of stairs, there's as we know, a ground reaction force in the vertical direction is always going to be positive. So the force is obviously in the positive direction. She wants to go up, obviously. So her vertical direction, her displacement, is also positive. Remember what I said earlier in the previous slide, work is the product of force and displacement. Because force and displacement going up are in the same directions, she's created positive work. Now look at coming back down. The ground reaction force, or real specifically her net force, is in the still in the positive direction, but she's moving in the downward direction here. So therefore, force and displacement are in the opposite direction, and subsequently, work is negative. So negative work is performed going down. I'm sorry, positive work is performed going up, while negative work is performed coming down. The way you can think of it, just think about muscle contraction. Going up, what do you think her muscles, more specifically, what do you think her quadriceps are doing when she's negotiating up the stairs? Well, look at quadriceps. Quadriceps extend knee. Does she extend her knee when she goes up the stairs? Yes. So therefore, those knee extensors are concentrically contracting. Why? Because they're shortening while the contractile force is being applied. So therefore, force and contractile velocities are in the same direction. So therefore, those muscles are generating energy. You're generating a change in her center of mass moving upward. So that's positive work. Coming back down, it's the other way around. So there's those same muscles are contracting still, but this time they're doing what? They're lengthening. So we call that eccentric muscle contraction. Those muscles are absorbing energy. Gravity wants to take Jane's center of mass towards the center of the earth. What's slowing that down? Well, it's her muscles, her quadriceps, her gastroc, her hip flexors. All of those combine. Sorry, not her hip flexors, her hip extensors. All of those combine create a situation in which her system is absorbing, her muscles are absorbing energy. So the way you can think about energy absorption is think of muscle contraction. That's eccentric muscle contraction. Think of all the various ways that we decelerate something. When you land from a jump, which we're going to talk about later on in this module, you're essentially absorbing energy. Why? Because you're decelerating. You're trying to absorb the energy of impact. The cushioning in your shoes, your running shoes, that in effect is energy absorption, because it is also absorbing or slowing down impact force in that case. So they're performing negative work for energy absorption, positive work for energy generation. Now let's take a look at the math behind this. It's actually pretty straightforward. So in this example, Jane has a mass of 60 kilos. If we had force platform on each one of these steps, and we're able to measure ground reaction force, we found in this example that each ground reaction force step is 1500 newtons. Each of those steps has a height of 30 centimeters. Now, very important, according to Newton's second law, that acceleration is directly proportional to the net force, as shown here. So we have to calculate the net force, which really is just the sum of the ground reaction force and her weight. It's 1500 newtons minus 589 newtons. Why? Because gravity is negative 9.81 meters per second squared. So therefore, her net force for each step is 911 newtons. So let's calculate the work going up. As I mentioned earlier, work is the product of net force times displacement. Because there are 10 steps, we have to multiply each work load, if you will, by 10. So 911 newtons, that's the net force, multiplied by the height of the step, multiplied by 10 steps. So the total work going up is positive 2,743 joules. That's what J is. Coming back down, because it's the same displacement, except this time it's negative, you find that the total negative work is negative 2,743 joules. So therefore the total mechanical work is 0, which makes sense because she ended up in the exact same position after she went up the stairs and come back the stairs. Exact same vertical position, I should say. So total mechanical work is 0. However, it doesn't make any sense. We know that she obviously used up energy to go up and come back down. So another way to express the work or the energy change of, say, looking at a flight of stairs, going up a flight of stairs, is looking at the mechanical energy expenditure, MEE. And all it is just the sum of the absolute values of the negative and positive work. In this case, the total mechanical energy expenditure is 5,468 joules. Now, the rate at which work is performed is known as power. So you guys know this. So power is the change in energy or mechanical work over a certain time interval, and we measure that in what's known as watts. So if you look at the units here, you have work in joules divided by time in seconds. That's joules per seconds, or what was otherwise known as a watt. So we measure the change in energy over time as power. A perfect example is looking at a power lifter performing a snatch or a power clean. We want to know how much power is generated or absorbed by this power lifter. We need to know the load, how much force is generated, and the speed at which she lifts or performs the actual snatch or power clean. And we can measure that using power. And in fact, there are apps out there that will do this for you. It's pretty. So if you're interested in some of the biomechanical research specific for strength and conditioning, they'll mention power or mechanical power quite a bit. So in the next video, we'll talk a little bit more about the first law of thermodynamics and the work energy theorem.